What if I told you the universe is hiding terrifying secrets? From invisible forces to colossal explosions, the cosmos is filled with phenomena that challenge our understanding and spark our curiosity. In this video, we will encounter cosmic nightmares like black holes, rogue planets, and gamma-ray bursts, revealing their awe-inspiring power and potential dangers. Stay with us as we navigate the cosmic horrors that lurk in the vastness of space, waiting to be uncovered. Prepare yourself for the most frightening and fascinating aspects of the universe that might just keep you up at night. Black holes are among the most mysterious and terrifying objects in the universe. Formed from the remnants of massive stars that have ended their life cycles in supernova explosions, black holes possess gravitational pulls so strong that not even light can escape once it crosses the event horizon. This invisible boundary marks the point of no return, beyond which the escape velocity exceeds the speed of light. The most common types of black holes are stellar mass black holes, which are typically 5 to 20 times the mass of our Sun. There are also supermassive black holes found at the centers of galaxies, including our own Milky Way. These behemoths can be millions to billions of times more massive than the Sun. One of the most terrifying aspects of black holes is their ability to distort space and time. According to Einstein's theory of general relativity, the immense gravity of a black hole warps the fabric of space-time, causing time to slow down near the event horizon. This phenomenon, known as time dilation, means that an observer near a black hole would experience time at a slower rate compared to someone far away. Black holes also generate intense tidal forces, which are caused by the difference in gravitational pull on different parts of an object. If an astronaut were to approach a black hole, they would experience spaghettification, where they would be stretched and torn apart due to these extreme tidal forces. Additionally, black holes can have strong electromagnetic effects. As they consume surrounding matter, they can form accretion disks that heat up to millions of degrees, emitting X-rays and gamma rays. These emissions can be detected by astronomers and provide indirect evidence of a black hole's presence. Despite their fearsome reputation, black holes play a crucial role in the evolution of galaxies and the universe. Their gravitational influence can trigger star formation, and they help regulate the growth of galaxies by merging and accumulating mass over time. In essence, black holes are both fascinating and frightening, embodying the extremes of physics and the unknown depths of our universe. Gamma-ray bursts, GRBs, are the most energetic events in the universe, capable of releasing more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifespan. These bursts of gamma rays, the most powerful form of electromagnetic radiation, can originate from two primary sources: the collapse of massive stars and the merger of neutron stars. When a massive star runs out of nuclear fuel, its core collapses, forming a black hole or neutron star. This process, known as a supernova or hypernova, can generate a long-duration GRB, lasting from a few seconds to several minutes. Alternatively, short-duration GRBs, which last less than 2 seconds, are believed to result from the collision and merger of binary neutron stars or a neutron star with a black hole. These events create intense magnetic fields and accelerate particles to near-light speeds, producing the powerful gamma rays. The gamma rays emitted in a GRB are focused into narrow jets that travel at nearly the speed of light. If one of these jets is directed towards Earth, we can detect it with our gamma-ray observatories. The initial burst is followed by an afterglow, which emits X-rays, ultraviolet, optical, infrared, and radio waves as the jets interact with surrounding material. The potential threat of GRBs to life on Earth cannot be underestimated. If a GRB were to occur within our galaxy and its jet were pointed directly at us, the intense gamma radiation could strip away the ozone layer, exposing the planet to lethal levels of ultraviolet radiation from the Sun. This could lead to mass extinctions and severe climate changes. Fortunately, GRBs are rare, and the odds of one occurring close enough to affect Earth are extremely low. Despite their destructive potential, GRBs also offer valuable insights into the processes of star formation, black hole creation, and the behavior of matter under extreme conditions. By studying GRBs, scientists can learn more about the early universe, as these bursts often originate from distant galaxies, providing glimpses into cosmic events that occurred billions of years ago. Rogue planets, also known as interstellar or free-floating planets, are planetary bodies that drift through space without being bound to any star. Unlike planets in our solar system that orbit the Sun, rogue planets travel through the galaxy independently, untethered by the gravitational pull of a star. Their existence challenges our understanding of planetary formation and dynamics. The formation of rogue planets is a subject of ongoing research and debate. They could form in a protoplanetary disk around a young star, similar to planets in our solar system, but are later ejected due to gravitational interactions with other planets or passing stars. Alternatively, they might form directly from the collapse of a gas cloud, similar to how stars form, but on a smaller scale. Rogue planets are elusive and difficult to detect due to their lack of a host star. Traditional methods of planet detection, such as the transit method or radial velocity, rely on the presence of a star. However, astronomers can detect rogue planets through gravitational microlensing, where the planet's gravity acts as a lens, magnifying the light from a distant star behind it. This method has led to the discovery of several candidate rogue planets. The conditions on rogue planets are harsh and varied. Without the warmth of a star, their surfaces are extremely cold, plunging to temperatures near absolute zero. However, some rogue planets might retain internal heat generated from their formation or from radioactive decay, potentially allowing for subsurface oceans beneath thick ice layers. Rogue planets could also pose a potential threat to planetary systems. If a rogue planet were to pass through a star system, its gravitational influence could disrupt the orbits of planets, moons, and other objects, potentially causing chaos. Despite their cold and dark nature, rogue planets have sparked interest in the search for extraterrestrial life. If a rogue planet has a thick atmosphere or subsurface ocean, it might provide the necessary conditions for life to exist, even in the absence of sunlight. In essence, rogue planets are fascinating and mysterious objects that challenge our understanding of planetary science. They highlight the dynamic and often chaotic nature of the cosmos, reminding us of the vast and varied possibilities within our galaxy. Supernovae are among the most dramatic and violent events in the universe, marking the explosive death of a star. These colossal explosions release an immense amount of energy, often outshining entire galaxies for brief periods, and play a crucial role in the cosmic cycle of matter and energy. There are two main types of supernovae, Type 1 and Type 2. Type 1 supernova occur in binary star systems where a white dwarf star accumulates matter from its companion star. When the white dwarf's mass exceeds a critical limit, it undergoes a thermonuclear explosion, completely obliterating the star. Type 2 supernova occur in massive stars, typically more than 8 times the mass of the Sun, that have exhausted their nuclear fuel. The core collapses under gravity, resulting in a rebound effect that propels the outer layers into space. The aftermath of a supernova can lead to the formation of neutron stars or black holes, depending on the mass of the original star. Neutron stars are incredibly dense remnants composed mostly of neutrons, with a mass comparable to that of the Sun but compressed into a sphere only about 20 kilometers in diameter. If the core is massive enough, it continues to collapse into a black hole, an object with gravity so strong that not even light can escape. Supernovae are not only spectacular but also essential for the enrichment of the interstellar medium. The explosive force of a supernova disperses elements like carbon, oxygen, and iron, created during the star's life and in the explosion itself, into space. These elements are critical for the formation of new stars, planets, and even life. In fact, the heavy elements that make up Earth and our bodies were forged in the cores of ancient stars and distributed by supernovae. The intense radiation from a nearby supernova could potentially affect life on Earth, but such events are rare and usually occur at safe distances. However, historical records and scientific evidence suggest that supernovae have been observed and documented by ancient civilizations, highlighting their impact on both astronomy and culture. Dark matter is one of the most enigmatic components of the universe, accounting for approximately 27% of its total mass and energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. The concept of dark matter emerged in the 1930s when astronomers observed that galaxies were rotating faster than could be explained by the visible mass alone. This discrepancy suggested the presence of an unseen mass providing the necessary gravitational pull. Further evidence came from the study of galaxy clusters and the cosmic microwave background radiation, which also indicated a significant amount of unseen matter. Dark matter is believed to be composed of non-baryonic particles, meaning it is not made of protons, neutrons, and electrons that constitute ordinary matter. The leading candidates for dark matter particles are weakly interacting massive particles, WIMPs, and axions. WIMPs interact through gravity and the weak nuclear force, making them incredibly difficult to detect. Axions are hypothetical particles that could solve certain problems in quantum chromodynamics and also account for dark matter. Scientists use various methods to search for dark matter. Direct detection experiments aim to observe dark matter particles interacting with ordinary matter in highly sensitive detectors placed deep underground to shield them from cosmic rays and other background noise. Indirect detection looks for signals of dark matter particles annihilating or decaying into standard particles like photons or neutrinos. Particle accelerators, such as the Large Hadron Collider, attempt to create dark matter particles through high-energy collisions. Dark matter plays a crucial role in the formation and evolution of cosmic structures. It acts as a gravitational scaffold around which galaxies and galaxy clusters form. Without dark matter, the observed distribution of galaxies and the large-scale structure of the universe would be very different. Its presence helps explain the observed gravitational lensing effects, where light from distant objects is bent around massive dark matter concentrations. Despite extensive efforts, the exact nature of dark matter remains one of the most significant unsolved mysteries in astrophysics. Understanding dark matter is crucial for a complete theory of cosmology and particle physics. Solving this mystery could lead to new insights into the fundamental nature of matter and the universe itself. Neutron stars are the remnants of massive stars that have undergone supernova explosions, leaving behind incredibly dense and compact cores. These stellar remnants are among the densest objects in the universe, with masses comparable to that of the Sun but compressed into a sphere only about 20 kilometers in diameter. The formation of a neutron star begins when a star with a mass between 8 and 20 times that of the Sun exhausts its nuclear fuel. The core collapses under gravity, causing protons and electrons to combine into neutrons, resulting in a dense ball of neutrons. The outer layers of the star are expelled in a supernova explosion, while the core is compressed to extreme densities, around 10 circumflex 17 kilograms per cubic meter. Neutron stars exhibit intense gravitational and magnetic fields. The gravitational field at the surface is about 2 billion times stronger than that on Earth, causing significant warping of spacetime. The magnetic fields of neutron stars are also extraordinarily strong, often trillions of times stronger than Earth's magnetic field. These magnetic fields can accelerate particles to near-light speeds, producing intense radiation. One of the most fascinating phenomena associated with neutron stars is pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, and if aligned with Earth, they can be detected as regular pulses of radiation. Pulsars can spin at incredibly high speeds, with some rotating hundreds of times per second. Neutron stars can also merge in a cataclysmic event known as a neutron star merger. These mergers produce gravitational waves, ripples in space-time, that can be detected by observatories like LIGO and Virgo. The collision also results in a kilonova, an explosion that produces heavy elements such as gold and platinum, contributing to the cosmic abundance of these elements. Additionally, neutron stars provide a unique laboratory for studying the properties of matter under extreme conditions. The densities and pressures inside a neutron star are far beyond what can be replicated on Earth, offering insights into the behavior of nuclear matter and the fundamental forces at play. Despite their small size, neutron stars have a profound impact on their surroundings. They can strip material from companion stars, forming X-ray binaries that emit powerful X-rays as the material is heated to extreme temperatures. The study of neutron stars helps astronomers understand the life cycles of stars, the behavior of matter at nuclear densities, and the dynamics of binary star systems. Space debris, also known as space junk or orbital debris, consists of defunct human-made objects in Earth's orbit. These include spent rocket stages, defunct satellites, fragments from collisions, and other discarded materials from past space missions. As the number of space missions has increased, so has the amount of debris, posing significant risks to both current and future space activities. The primary sources of space debris are defunct satellites, rocket parts, and debris from collisions. For instance, in 2007, China conducted an anti-satellite missile test, destroying a defunct weather satellite and generating over 3,000 pieces of debris. In 2009, an active Iridium communications satellite collided with a defunct Russian satellite, producing another significant cloud of debris. Space debris travels at extremely high speeds, up to 28,000 kilometers per hour, 17,500 miles per hour, in low Earth orbit, LEO. At such velocities, even small fragments can cause significant damage to active satellites and spacecraft. A collision with a piece of debris as small as a paint fleck can create pits and craters in spacecraft surfaces, while larger pieces can cause catastrophic failures. The presence of space debris increases the risk of the Kessler syndrome, a scenario proposed by NASA scientist Donald Kessler, in which the density of objects in LEO becomes high enough that collisions between objects create a cascade effect, generating more debris and leading to further collisions. This runaway scenario could render certain orbits unusable for satellite operations and space exploration. Efforts to mitigate the space debris problem include improving the design of spacecraft to minimize the creation of debris and developing technologies for debris removal. Strategies include using materials that reduce fragmentation during collisions, implementing better end-of-life disposal methods for satellites, and designing missions to deorbit defunct satellites and rocket stages safely. Active debris removal, ADR, is another critical area of research. Proposed methods for ADR include using robotic arms, harpoons, nets, or even laser systems to capture and deorbit debris. While these technologies are still in the experimental stages, they hold promise for reducing the growing threat of space debris. International cooperation is essential for addressing the space debris problem. Organizations like the Interagency Space Debris Coordination Committee, IADC, work to develop guidelines and best practices for space debris mitigation. Additionally, national space agencies and private companies are increasingly aware of the importance of sustainable space operations. Solar flares are powerful bursts of radiation emanating from the sun, caused by the sudden release of magnetic energy stored in the sun's atmosphere. These intense emissions can affect space weather, impacting satellite operations, communication systems, and even power grids on Earth. Solar flares occur in the sun's outer atmosphere, known as the corona, and are often associated with sunspots, which are regions of intense magnetic activity on the sun's surface. When the magnetic fields near sunspots become twisted and entangled, they can suddenly release energy in the form of a solar flare. This energy release accelerates charged particles and heats the surrounding plasma to millions of degrees, emitting radiation across the electromagnetic spectrum, including X-rays, ultraviolet light, and radio waves. Solar flares are classified based on their X-ray brightness in the wavelength range of 1 to 8 angstroms. They are categorized into 5 classes: A, B, C, M, and X, with X-class flares being the most intense. Each class has a logarithmic scale, meaning an X-class flare is 10 times more powerful than an M-class flare. The effects of solar flares on Earth can be significant. High-energy particles and radiation from flares can interact with Earth's magnetosphere, leading to geomagnetic storms. These storms can disrupt satellite communications, GPS signals, and radio transmissions. The increased ionization in the Earth's ionosphere can degrade high-frequency radio signals, which are crucial for aviation and maritime operations. Solar flares also pose risks to astronauts in space. The intense radiation can penetrate spacecraft, potentially harming astronauts if they are not adequately shielded. Solar flares can also endanger future manned missions to the Moon or Mars, where astronauts will be outside the protection of Earth's magnetic field. Another potential impact of solar flares is on power grids. The induced electric currents from geomagnetic storms can overload transformers and other electrical infrastructure, leading to widespread power outages. A notable example of this occurred in 1989 when a powerful geomagnetic storm caused by a solar flare-induced blackout in Quebec, Canada. Scientists monitor solar activity using a variety of space-based and ground-based observatories. Satellites like NASA's Solar Dynamics Observatory, SDO, and the Solar and Heliospheric Observatory, SOHO, provide real-time data on solar activity, allowing for the prediction and mitigation of space weather effects. Cosmic rays are high-energy particles originating from outer space that travel at nearly the speed of light and strike the Earth's atmosphere. They consist mostly of protons, but also include heavier atomic nuclei and electrons. These particles are fascinating and potentially hazardous due to their high energy and ability to penetrate matter. Cosmic rays can be classified into two main categories: galactic cosmic rays, GCRs, and solar cosmic rays. GCRs originate outside the solar system, primarily from supernovae, which are massive star explosions. These events accelerate particles to high energies and eject them into the galaxy. Solar cosmic rays, on the other hand, are produced by the Sun, particularly during solar flares and coronal mass ejections, CMEs. When cosmic rays enter the Earth's atmosphere, they collide with atoms and molecules, creating showers of secondary particles. These secondary particles include pions, muons, and neutrinos, which further interact with the atmosphere. The interactions produce a cascade effect, resulting in a variety of particles that can be detected at the ground level. The energy of cosmic rays spans a wide range, from a few million electron volts, MeV, to over 10 circumflex 20 electron volts, EV. The highest energy cosmic rays are extremely rare, but possess energies millions of times greater than those produced by the most powerful human-made particle accelerators. Cosmic rays pose several challenges and risks. For astronauts and space missions, cosmic rays can penetrate spacecraft and human tissue, increasing the risk of cancer and other health issues. This is a significant concern for long-duration missions, such as those to Mars, where astronauts will be exposed to higher levels of cosmic radiation compared to low Earth orbit. On Earth, cosmic rays can interfere with electronic systems, causing data corruption in computers and other sensitive equipment. This effect, known as a single-event upset, SEU, is particularly concerning for aerospace and satellite technology. Engineers design shielding and error-correcting codes to mitigate these risks. Cosmic rays also play a role in atmospheric chemistry and cloud formation, potentially influencing the Earth's climate. Some theories suggest that variations in cosmic ray flux could affect cloud cover and, consequently, climate patterns. However, this area of research remains controversial and is an active topic of scientific investigation. To study cosmic rays, scientists use ground-based observatories, such as the Pierre Auger Observatory in Argentina, and space-based instruments, like the Alpha Magnetic Spectrometer, AMS, on the International Space Station. These instruments help researchers understand the origins, composition, and behavior of cosmic rays. The Great Attractor is a gravitational anomaly located in the Laniakea supercluster, a massive concentration of galaxies, including our Milky Way. This mysterious region exerts a powerful gravitational pull, influencing the motion of galaxies over vast distances. The nature and exact composition of the Great Attractor remain subjects of intense scientific investigation and speculation. Discovered in the 1970s through observations of galaxy motions, the Great Attractor is located approximately 250 million light-years from Earth in the direction of the Centaurus and Hydra constellations. Galaxies, including our own, are moving towards this region at significant speeds, indicating a substantial mass concentration exerting a strong gravitational pull. The zone of avoidance complicates the study of the Great Attractor. This region of the sky is obscured by the Milky Way's dense plain, filled with stars, dust, and gas, making it difficult to observe objects behind it. As a result, direct observations of the Great Attractor are challenging, requiring advanced techniques and instruments to penetrate this dense region and gather data. The mass of the Great Attractor is estimated to be equivalent to tens of thousands of Milky Way galaxies. However, its exact composition is still unclear. It is believed to consist of a mix of visible matter, such as galaxies and galaxy clusters, and dark matter, which does not emit or absorb light but exerts gravitational influence. The interaction between these components contributes to the overall gravitational pull observed in this region. The existence of the Great Attractor has significant implications for our understanding of cosmic structure and dynamics. It highlights the uneven distribution of mass in the universe and the complex gravitational interactions shaping the large-scale structure of the cosmos. The movement of galaxies towards this massive concentration provides insights into the underlying distribution of dark matter, which is thought to play a crucial role in cosmic evolution. Further study of the Great Attractor involves mapping the velocities and positions of galaxies with greater precision and developing more advanced models of cosmic structure formation. Upcoming observational projects and improved technology, such as the James Webb Space Telescope, are expected to shed more light on this enigmatic region. Quasars, or quasi-stellar objects, are among the most luminous and energetic objects in the universe. Powered by supermassive black holes at the centers of distant galaxies, quasars emit enormous amounts of energy as they accrete matter, outshining entire galaxies and providing critical insights into the early universe. The discovery of quasars in the 1960s revolutionized our understanding of the cosmos. Initially identified as star-like points of light emitting strong radio waves, further analysis revealed their extraordinary luminosity and high redshifts, indicating they were incredibly distant and ancient. Quasars are typically billions of light-years away, allowing astronomers to observe them as they were in the early stages of the universe. At the heart of a quasar lies a supermassive black hole, with masses ranging from millions to billions of times that of the Sun. Surrounding the black hole is an accretion disk of gas and dust, spiraling inwards and heating up due to intense gravitational and frictional forces. This process releases vast amounts of electromagnetic radiation across the spectrum, from radio waves to gamma rays. The extreme luminosity of quasars, often outshining their host galaxies, makes them visible across vast cosmic distances. A single quasar can emit more energy than hundreds of billions of stars combined. This brightness enables astronomers to use quasars as beacons to study the intergalactic medium and the large-scale structure of the universe. Quasars also exhibit variability in their brightness over various timescales, from days to years. These fluctuations provide insights into the size and dynamics of the region close to the black hole. For example, rapid changes in brightness suggest that the emission region is relatively compact, consistent with the vicinity of a supermassive black hole. One of the remarkable aspects of quasars is their role in understanding galaxy evolution. The intense radiation from quasars can affect their host galaxies by heating interstellar gas and driving powerful winds. These outflows can regulate star formation by dispersing gas, a process known as feedback, which is crucial for shaping the growth and structure of galaxies. Quasars are also invaluable tools for probing the distant universe. Their light travels across vast distances, passing through intervening matter and revealing the properties of the cosmic web. By analyzing the absorption lines in quasar spectra, astronomers can study the distribution of intergalactic gas, the abundance of elements, and the presence of dark matter. The study of quasars continues to advance with the development of new observational techniques and instruments. High-resolution imaging and spectroscopy, particularly with telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, are expected to uncover more details about quasar environments and their role in cosmic history. Magnetars are a type of neutron star with the most powerful magnetic fields known in the universe, measuring up to 1,000 trillion times stronger than Earth's magnetic field. These exotic objects result from the collapse of massive stars during supernova explosions, leaving behind incredibly dense remnants with intense magnetic properties. The formation of a magnetar begins similarly to other neutron stars. When a massive star, typically around 10 to 25 times the mass of the Sun, exhausts its nuclear fuel, its core collapses under gravity. This collapse results in a neutron star, a dense core primarily composed of neutrons. However, in the case of a magnetar, the star's magnetic field is amplified to extreme levels during the collapse, possibly due to rapid rotation and the dynamo effect. Magnetars exhibit several unique and extreme phenomena due to their magnetic fields. One of the most notable is their emission of soft gamma-ray and X-ray bursts. These bursts occur when the magnetic field undergoes sudden reconfiguration or when crustal movements on the magnetar's surface release magnetic energy. The intense magnetic fields can stress and crack the crust, causing starquakes that release vast amounts of energy. The magnetic field of a magnetar also affects its surroundings. It can influence nearby matter, creating complex and dynamic environments. The strong magnetic field can strip electrons from atoms, ionizing surrounding material and producing highly energetic particles. These particles can emit X-rays and gamma rays, making magnetars some of the most luminous X-ray sources in the sky. Magnetars are known for their relatively short active lifespans. The intense magnetic fields gradually decay over time, usually within about 10,000 years, causing a decline in their X-ray and gamma-ray emissions. As the magnetic field weakens, the magnetar transitions into a more typical neutron star state. One of the most fascinating aspects of magnetars is their potential link to fast radio bursts, FRBs, mysterious and brief flashes of radio waves observed from distant galaxies. Some theories suggest that FRBs may originate from magnetars, as their extreme magnetic environments could produce the necessary conditions for these powerful radio emissions. Magnetars also provide valuable insights into the physics of extreme environments. Studying them helps scientists understand the behavior of matter under intense magnetic fields and high densities, conditions that cannot be replicated on Earth. They also offer clues about the life cycles of massive stars and the processes leading to their explosive deaths. Void regions, or cosmic voids, are vast, empty spaces between galaxies and galaxy clusters, making up a significant portion of the universe's large-scale structure. These regions are characterized by their extremely low density, containing only a few galaxies, if any, compared to the densely packed areas of the cosmic web where galaxies clustered together. Cosmic voids were first identified in the late 20th century through large-scale galaxy surveys. These surveys revealed that galaxies are not evenly distributed throughout the universe, but are instead arranged in a web-like structure, with dense clusters, filaments, and vast empty spaces in between. Voids can span tens to hundreds of millions of light-years across, making them some of the largest structures in the universe. The formation of voids is a natural consequence of the gravitational evolution of the universe. Shortly after the Big Bang, the distribution of matter was relatively uniform, with slight density fluctuations. Over billions of years, gravity amplified these fluctuations, pulling matter into denser regions and leaving behind empty spaces. As a result, voids expanded while galaxies and galaxy clusters formed in the denser regions, creating the large-scale structure we observe today. Despite their emptiness, voids play a crucial role in cosmology and our understanding of the universe. They provide a complementary perspective to studies of dense regions, offering insights into the distribution of dark matter and the properties of dark energy. The low-density environments of voids make them excellent laboratories for testing cosmological models and the behavior of dark energy, which is believed to drive the accelerated expansion of the universe. Voids also influence the motion of galaxies and the propagation of light. Galaxies near voids experience a gravitational pull towards denser regions, affecting their velocities. This motion, known as cosmic flow, helps astronomers map the distribution of mass in the universe. Additionally, the light from distant galaxies and cosmic microwave background radiation passing through voids can be slightly redshifted due to the lower gravitational potential, an effect known as the integrated Sachs-Wolf effect. The study of voids is advancing with increasingly detailed galaxy surveys and simulations. Instruments like the Sloan Digital Sky Survey, SDSS, and upcoming projects like the Large Synoptic Survey Telescope, LSST, are providing high-resolution maps of the large-scale structure, allowing for more precise measurements of void properties and their impact on cosmology.